Hello and welcome to another episode of Blast from the Past, where we'll be discussing previous year questions from JEE Advanced. So today's question is actually, pretty old. It's from the 90s. It is a question from Gravitation. So let us check the question. We have a solid sphere of uniform density and radius 4 units. So this is 4 units. Centered at the origin, and two spherical cavities are made centered at -2, 0, 0 and 2, 0, 0. So two spherical cavities symmetrically placed along the x-axis, each of radius 1 unit. So we are asked to check the gravitational field due to the remaining portion of the sphere. First at the center, then a point inside, that is at the point B, inside the spherical cavity here. And we are also asked to find out the gravitational potentials. Okay. So in order to solve this question, you should know the principle of superposition, right? So what we do is, first we think or we imagine that the sphere is complete, right? There is no cavity. Here also a uniformly dense mass is filled. So there is no cavity. So in that case, what would have been the field at the center? Right? We know that in the case of a uniform solid sphere, field at the center is 0, right? Now that field I can imagine to be a vector sum of, say, vector sum of field due to A part, right? Field due to the imagined sphere at A. There was no sphere at A, we have imagined the sphere at A, right? So field due to A plus field due to B plus field due to the remaining part, whatever part is remaining. Now this is the actual field that is required, right? This is the only thing that is really existing. So field due to the remaining part is what we want. But we know that all of this together will be 0. That is, if the sphere was complete, the field would have been 0. Right? Now by symmetry, I can say that the field due to A will exactly cancel out the field due to B at the center. If you've taken a point at the center, the origin, A's influence will be cancelled out by B. So f of A, field due to A, is equal and opposite to field due to B. Right? So this portion will cancel out and I will get field due to the remaining portion, that is the required field, as 0. Okay. Now coming to the second part. Find the gravitational force at the point 2, 0, 0. Right? Again, let us consider this point. Again, applying superposition. So if the entire sphere was there, what would have been the field at a point inside the sphere? That is at point B. What would have been the field? The entire sphere was present. It is given by the formula minus Gm by A cube into R, right? Where A is the radius of the entire sphere and R is the distance of the point where we are concerned from the center. We know this formula, right? So we can just apply that and the principle of superposition. So the field due to A plus the field due to the imagined sphere at B plus the field due to the remaining part. This should be this, right? Minus Gm by, I can directly plug in the values. Here the radius of the sphere is 4. So I can use 4 and this distance 4 cube. And this distance is, we know this distance is 2. Right? So in order to evaluate the field due to remaining part, I need to find out f of field due to A and field due to B. So what will be the contribution of B? What will be the field due to B at the center of, or field due to the sphere at this point B? It will be 0 because it is located exactly at the center of the sphere, right? It is located at the center of the small sphere. So the contribution from B will be 0. Now, if I can find out the contribution due to A, then indirectly I'll get the field due to the remaining part, and that is what is required. Okay. Now, in order to answer this question, you really need not find out the field, right? You can also argue from the principle of symmetry, or lack of symmetry rather, that this field at point B will not be 0. So this option will not be correct. So this is a multi-correct question. We have to select the correct option. So first option is correct and second option is wrong. But I'm going to go a step further and find out the field, because in the coming papers we can expect a question like this where you're asked to find out the field, right? So this is how we'll proceed. Now, how to find out the field due to A? The field due to the imagined sphere, this imagined solid sphere at A, what influence or what field it is creating at B? Now, for that, I can just imagine the solid sphere to be a point mass centered at A, and I can just take the distance, right? This is going to be 2 plus 2, 4. So the field due to A will be minus G small m. Now, what is going to be the mass of the imagined sphere? If the bigger mass I have taken as capital M, then the smaller masses which I use to fill the cavity, right? The cavity has been filled with small m's. So that will be, I can say that will be 1 by 64th, right? It will be 1 by 64 times. So I can directly plug in that Gm by 64 and distance square. Distance will be 2 plus 2, 4. I'll have 4 square. Right. So this plus F remaining is equal to, this will be minus Gm by 32. Right? So on rearranging, I will get the field due to the remaining part. So this comes out to be F is equal to, the required field is equal to minus Gm by 32 plus Gm by, this will come out to be 1024. Right. So on simplifying, this will come out to be minus 31 Gm by 102. Right. So we have actually tried and solved. We've got the value of the field. Clearly not equal to 0. We have found out the value of the field. Right. Now we could do this because it was a point at the center of the, second spherical cavity. Now if it was somewhere else in the cavity, then we will have to, the FB contribution will also come into play. So it will be a little more complicated, but still doable. Right? Okay, so that is about field. Now we will try to find out the potentials. Right? So let me just clear this out. What will be the potential? What will be the gravitational potential due to this arrangement on a circle of radius 6 units in a plane it is in the YZ plane, right? The cavity is along the x-axis and the plane or the circle we are considering is like this. Circle is like this in the YZ plane. So I can draw it like this. And it is a bit too long. We reduce the size. Okay. Circle like this. Circle like this in the YZ plane, right? It's in the YZ plane. So to answer this question, we need not actually calculate the potential, but we'll do it later. By symmetry, you can say that all the points on the circle are located symmetrically. So the gravitational potential has to be same. But how can we calculate this gravitational potential? Let us go a step further and calculate the gravitational potential. Right? So here again, we can use the principle of superposition. So to calculate potential. Potential is equal to potential due to the entire solid sphere. So I am imagining a solid sphere without the cavities, right? So that potential is equal to potential due to the imagined sphere at A plus potential due to the imagined solid sphere. I filled the cavity with mass B. So the imagined mass B plus the potential due to the remaining part. So this is our required potential, right? This is what we have to find out. So how to proceed? Now, what is the LHS? What can I say about this potential? That is the potential, gravitational potential. If the entire mass was present, there is no cavity, a big capital M mass is there, uniform solid sphere is there, and the circle that we have considered, these points are outside the solid sphere. So if the points are outside the solid sphere, then how can we find out the potential? It is like this mass is concentrated at the center. It's like that, no? We can take it as a point mass at the center. So in that case, potential will be minus Gm by R. What is the distance? This is the radius of the circle. Radius of the circle constructed. So that is equal to 6. So this is the potential. If the entire sphere was there, but the entire sphere is not there. So we have to find out potential due to remaining part. Right. So this is equal to VA plus VB plus VRE. Now what is VA? What is VA? Potential due to the imagined sphere at A. Because of this imaginary sphere that we have constructed at A, what will be the potential on this circle, right? So again, for the sphere, these points are outside of the sphere. So we can take it as a point mass located at the center. But now what is the distance? Distance of each point on the circle from the center, what will be the distance? If I take this as 2, this, you have to imagine, no, it is in the YZ plane. The circle is in the YZ plane. This is along X. So you go 2 units along the axis to get to the origin. Then we have to travel 6 units here, right? Radius is 6. So this distance is nothing but root of 2 square plus 6 square. This is root of, we have to imagine a right triangle here. So in the 3D, you have to imagine a right triangle. This is 2 square plus 6 square. So this distance is actually root of 40. This distance is root 40. Right? So what will be the potential due to A and potential due to B? It will be same, right? A, it's symmetrically located. So VA and VB will be same. So I can just write minus 2G. Instead of small m, I can substitute directly m by 64. And the distance. See, the distance here is, we've got it as root 40. Root 40 is the distance, right? Plus potential due to remaining. So you just need to rearrange this to get the potential due to the remaining sphere. This comes out to be minus gm by 6 plus gm by 32, and there will be a root 40. I can actually take out, can make it 64, right? So you can do the simplification. It comes out to be something like this. Okay. So I found out the gravitational potential on a circle, y square plus h square equal to 36. So this is anyway true. This is anyway true. Even without calculation, this is anyway true, right? Now, how to find out the gravitational potential on the circle y square plus h square equal to 4? Again, in order to check this option, it is going to be same at all points because of symmetry. So I can directly take this option. But how to find out the value of gravitational potential on the circle? Right. So this is a different circle. This is going to be like this. This is a circle well inside the sphere. Okay. The circle to be imagined is inside the sphere. So it is well outside these two small spheres, but well inside the larger sphere. So it is a circle like this. Now, how to find out the gravitational potential in this case? So in order to do this, we should know the formula for gravitational potential due to a uniform solid sphere. Due to a uniform solid sphere in a point inside the uniform solid sphere, right? So what is that value? Potential is given as minus 3gm by, minus gm by 2a cube 3a square minus r square, where a is the radius of the sphere. So this is the formula, minus gm by 2a cube 3a square minus r square. This is an often neglected formula, but for advanced they might ask this or a question linked to this, right? So I can directly apply this to find out the potential on a circle, right? So just apply the formula. So if the sphere was there, if there was no cavity, then I can say the total potential at a point on the circle is equal to, right, since it is located at a distance of 2 units, right? So I can say the total potential would have been minus gm by 2a cube, 2 into a cube, 4 cube, right? 3 into a square. Again, a square is 4 square minus r square. Where is the point located? So the point is located r is equal to 2. So 2 square. So this would have been the potential had the masses been present, had there been no cavities, this would have been the potential. Now this is equal to V due to A plus V due to B plus V due to the remaining part. Now to calculate VA, BB, by symmetry both will be equal, and VA and VB will be what? Because for this circle, for the points on this circle, A and B are spheres. These spheres are outside. So these imagined spheres are outside these points. So we can just approximate them as or use them as point masses located at the center and just use the formula minus 2 gm by 64. But what will be the distance? Again, we have to construct a right triangle here, right? The distance will be, so this is 2, this is 2. So distance will be 2 root 2. Distance is going to be 2 root 2. So I'll just put 2 root 2 here, right? So on rearranging, we will get, what will we get? This is minus gm by This is nothing but, here I will have 3 into 4 square. So this is going to be 44 by 2 into 64. So this becomes 22 by 64. Here I have 2 cancels. So this will be GM by 64 but root. So if I take GM by 64 outside, I will get 20 minus 22 plus 1 by. So this is the potential due to the remaining sphere. So it's a bit tedious to find out these values, but it can be asked, right? If they can ask this much, the coming exams, they can actually ask you to find out the values also. Okay, so now regarding the superposition principle, now I have done it in a very lengthy way, right? Superposition principle has been theoretically done and it has been done in a very lengthy way. But as a shortcut, we can use the idea of, putting negative mass, just like in electrostatics, where we can fill a cavity with a negative charge and approach the problem. We can do it in a similar way by adding negative mass, for the sake of doing the problem, right? So in that case, it will be slightly more simpler, but it's the same thing. It's the idea of superposition that we are using, right? So that's it for now. Please follow us for more updates. Thank you.